Hey everybody, my name is Nikolay. I'm from Russia, St. Petersburg, and I will tell about Node.js application diagnostics under the hood. First of all, sorry for my English. Instead of improving it, I spend a lot of time under the hood with debuggers. I work at Green Dynamics. I'm a full-stack developer, and in the retail domain, we do digital transformation for large US e-commerce companies using Node.js. And in order to create our solution successful, we devote a lot of time to diagnostics. And today, Node.js Diagnostics has a working group that deals with performance profiling, tracing, memory analysis, and postmortem debuggers. And to understand where we are now in diagnostics, I suggest you look at as a timeline, as a history, where I put the appearance of significant tools and highlighted several stages. The first stage, of course, starts from 2009, when Node.js was presented at JSConf. Cool. But the part of popular instruments appeared before the Node.js, though as system profiler, dtrace, perf, instruments, and they're still in use. After the Node.js appearance, began to appear tools from the first stage, heap dump, memory watch, node inspector, and basically those tools were effective in development and not in production. And also, do you remember there was a fork, IJS, which evolved more rapidly than Node.js itself? So community was divided. But since 2015, IJS and Node.js unite into fourth version. Community has a clear vector of development. And by this point, Node already used in production by large companies such as eBay, Alibaba, Amazon, and by our customers as well. And here is a need for debugging and profiling tools in production. We created flame graphs for profiling, and C++ debuggers were adapted for Node.js debugging. So only in the second stage, we've got the ability to debug and profile in production. But we were there in the first stage already, and it was funny and painful. From the 2017, I have highlighted the first stage on the timeline, which is mostly focused on improving Node.js performance, tracing internal components, and improving the quality of instruments. Here is a significant transition to turbofan, appearance of async hooks. So it looks like today we have a lot of useful tools, but most of them still are external and require better functionality with less performance overhead. And summarize the past in diagnostics. Node.js was mostly focused on performance, and there were reasons for that. We often didn't have enough functionality, and each time we transitioned to a new version of Node.js, we faced it with the fact that we lose support of many useful tools. So we had to choose. Either we go with a new version, which is faster, but we lose support of useful tools, or we stay with the old, slow, but with the tools. And our applications, Node.js applications, web UI backend for front-end, and microservices are located in the center of large enterprise architecture, where integrate with multiple systems such as CDN, different databases, services, and the problem can come here from anywhere. And in the days of highload, such as Black Friday, when company make a huge profit, each mistake costs $1,000 per minute. And if there is an error in Node.js application, it's necessary to choose a strategy and tools as soon as possible and prepare the hard fix. And today I will show you how we do that in certain examples in case of errors, performance loss, and memory leaks in production. So let's go to the debugging. There are several reasons for debugging in production. Uncut exception kill your process. Difficult reproducible errors, and you don't have enough information from your logs, and actually you cannot log everything. Production environment features, and error doesn't reproduce locally, and you don't have a time. Let's move on to the simple example. We have a controller which calls service that work with REST API, and the error is thrown in the controller and application crashes. And here is a simple implementation of product reservation. We have a product controller with a reserve method where user profile and reverse account data are extracted from the cookies. And since some user doesn't have reverse account, application throws an error, your application crashes, and so it's bad. But if we set the flag abort an uncut exception, in case of uncut exception, Node.js will create core dump, which is a dump of whole memory of the process that contains a heap dump and StackTrace before the crash. After that, your application restarts, you get access to production, to the dump, and read it with a debugger. The most relevant today is a llnode plugin for LLDB debugger. So, and to find the error, we need to do just 3 simple steps. So we need to get the StackTrace and find the last JavaScript operation, function, and read the source code of this function and get the input parameters, request and response. So let's repeat it with the core dumps. We have a core dump, and to read it, we need to run llnode and specify the path to the dump. After that, in debugger session, we get access to read StackTrace with the command to 8bt, which is a backtrace. And here we need to find the last.js function, which is stored in 6 frame. And here we see this is a reserve method of our product controller, and we have addresses to this object, incoming message, which is a request, response, and even to the function source code in the memory. So we need to read the source code of our function. So let's just get the address. And using command v8 inspect print source with address on function, we get the source code of this function out of the memory. After the reading source code, let's return back to the StackTrace and get the address of our request and extract it from the memory. And here it is. So this is our request. We did it with the command v8 inspect and use it address of request. And after that, we can repeat this command to get the cookies to figure out which profile doesn't have rewards and why our application crashes. So that's pretty simple. But it was a good StackTrace, informative StackTrace, and because we had all necessary information, we had an order of last functions with addresses to the request, response, or all object. But sometimes a framework error handler or incorrect customer error handling makes a trace uninformative. Consider this, the next example. So here, instead of pass exactly an rewards ID, we accidentally pass the whole rewards object. And now the error is thrown in the service in asynchronous mode, and we don't have a catch block here to catch the error. And to catch it, we use a subscription to Unhandled rejection event where we will do process abort to crash it to get the dump. And when we try to get the StackTrace of this dump, we will not find any necessary information. So we don't have request, response, and needed functions. So we don't have a StackTrace. And in this case, we need to work just with a heap dump, with the memory. And I'll show you how to do this. First of all, we need to get the requests from the memory. And we can find objects by the type using command find.js instances and specify incoming message. So those are requests in the dump, in the memory. But why there are so many? And which request crashes the process with all other requests that were there inside the event loop? And how to find it? And in this case, we use a unique request ID, which we store in the header in xTransaction ID, to find the right one. And we can get this value from our logs. And find which object has a reference to this string, to this value, with the command find refs -- string. And we have a headers object. So let's find the parent object of this header. And using command v8 find refs value and address of headers, we found the incoming message as a request that we need. Hi, Dave. So that was easy. Let's go deeper and imagine that this data is not enough for us, and we need to know local variables from other functions. For example, from the reserve service. There was a request to REST API and request to database, and the results were assigned to some local variable data. And we don't have any objects referencing to this data, how to find it. But we can find this object by values of its properties. For example, by rewards ID, user ID, or even by the name of some property, for example, rewards in store. So the main idea is here that we can find the objects not only from the last function before the crash. We can get them out of memory from all other functions with high probability that were executed before the crash. For example, from middleware, from policies, from controller, or other storage service and storage. And it helps a lot. And to get more information, we can use a node report. And in fact, the search for an error, it's like a data investigation, where after generated before the crash, report will say you what happened with your process by JavaScript and C++ StackTrace, where it was, and under what conditions by work of garbage collector, memory, and CPU. And logs will give you valuable hints. But core dump is not a silver bullet, and to create core dump on each error is not a good idea. Otherwise, the picture will be like this. We have a lot of errors in production, and you know the spell, not a bottleneck exception. So let the debugging begin. For each error is created core dump, 1 core dump, 2 core dump, 3 core dump, a lot of core dumps. And your boss is waiting for you, and she asks, hey buddy, we lose money. How much time do you need to solve this issue? And you think, where is my dump? So I call this situation core dump flood. Where is the problem? We need to have we need to follow to error handling best practices to have a centralized error handler with error selection logic. For example, I have a hard reproducible error, but I don't want to generate hundreds of identical core dumps and look for them among other. Or I don't want to create core dump and kill the process every time on error when I can handle it. And in this case, I use a gencore and Error Registry, which is a custom error selection logic, which makes decision, should it create core dump, or was for this error dump created already, or is this a hard reproducible error? And if it should, we use a gencore that makes fork of your main process and terminates it with a dump. And our main process continues serving traffic without accident. So that's pretty cool enough. And let's review the whole algorithm last time. So if the error is not caught, Node.js application generates a core dump, node report generates a report, and application restarts and continues serving traffic. But if the error was caught, error handler put available information to a log file, and error selection logic make decision, should it crash the process, should it generate a core dump, and if not, it continue serving traffic and handles the error, and if it should, it use gencore to make a process fork to terminate it with a dump, and our main process continues serving traffic. So after that, we just connect to production, get log and our core dump to debug it with llnode. Easy. So my suggestions: follow to error handler best practices. Call abort only in one place, in centralized error handler. Use a gencore to not kill your main process, and use a node report to have more information in case of unexpected crash. Track your ID using request IDs, for example, xRequest ID from Nginx or Zipkin headers, and avoid core dump flood. That was about debugging in production. So let's go to the performance profiling and search for memory leaks. And let's investigate the performance loss and memory leaks at an example of real situation. When after one of the releases, we got a huge performance decline just before the Black Friday Eve. And to figure out where is the problem, we can start with performance profiling using internal profiler of Node.js and tick processor to find the longest operation. But there is a good graphical representation of profiled traced stacks. It's called flame graph. And the main idea of it to find the widest block, because the wider block is, the more often it was during the sampling in CPU, so the longer it was performed. And on high-level overview, we can find that application spends 10% on retrieval data from API, 20% on lodash operation with that data. And the longest block is the server-side page rendering. It's about 65% of time. And it's a lot because it consists from custom helpers, partials, and templates with logic. And if we scroll up, we will see which operations are on CPU. Here is handlebars and is lodash merge, utils. And let's go deeper to lodash merge stacks. And if we zoom in, we will see there are a lot of white blocks of lodash, base merge operation, base merge deep, clone deep, for each cycle, and for data processing of product mapper. So we found that our helpers, logic and template, a lot of cycles, lodash, utils are our performance as a cause of loose performance. It's our bottlenecks. And to improve that, we did performance profiler with perf, Xerox, BCC tools, and what we did, we reduced CPU-intensive operations since they block our main process. Long cycles, JSON parse, lodash object merge, removed logic from view templates and helpers, especially custom helpers, and gradually implemented server-side rendering. And after those all improvements, our server-side rendering spends only about 15% of main time. And we reduced white blocks and increased our asynchrony of application execution. So my suggestions, performance should be a part of requirements every time. If you would like to add some library, third-party library or your library, you need to measure performance before and after, every time. Collect the measurement result archive, and profile on different environments, on stage environments, and monitor diagnostic tools' performance impact. But misfortune never comes alone. And with performance loss, we have a problem with memory consumption. And there are many ways how to identify memory leaks. We can do it with application monitoring tools like nsolid, New Relic, dtrace, perf, compare, heap dump. But I suggest you to focus on excessive garbage collection since it makes negative impact on performance. Look at this New Relic graph. The GC rate grows in a new space, young generation. And to get more information about garbage collection work, we can trace it using traces GC flag of Node.js. And here we see that memory consumption grows after each collection. And interval between collection is too short. That means that it's difficult to find them in the memory. And garbage collection performs very frequently. And by the duration of garbage collection, we see there are 16 milliseconds, 17, and they're more than 1 default millisecond. So that means that garbage collection spends more time to get the objects in the memory because of complex topology, complex graph of objects in the memory. And it spends more time to clean up the memory. And how to track which operations require memory allocation. And as we know, Node.js profiling result, traced stacks, it's a mix of JavaScript function and native V8 functions. So why not just keep track way back from garbage collection functions calls to JavaScript? So let's look at a simple implementation of flame graph. And on the left side, where CMS helper did insert, it used string replies, which required memory allocation for a new one use string. And after that, since memory allocation was failed, garbage collection called collect garbage. And what we can do, we can find Scavenge object slow, look at text representation command, and figure out by way back which JavaScript function required memory allocation and clean up the memory. So, and CMS helper is a problem. The same example with the product mapper, which did a map of big array. And since it required memory for new items and garbage collection called Scavenge object and allocation step. So as I said, we reduced our mappers, clones, big JavaScript cycles, and custom helpers. And in the result, after that, our memory doesn't grow, and garbage collection is little more than 1 default millisecond, but we think it's OK. And the same problem was in old generation, where is a long garbage collection. And to find missed closures or timers, usually we use a heap dump, we compare them, but I'll show you how to do the same with a core dump in case of fatal error when you get the core dump. So what we need to do, we need to get a report of all JavaScript objects inside the memory. We can do it with the command v8 find objects, JS objects. And large of incoming messages look suspicious. So let's figure out where those requests are located. So we need to get all of them from the memory, choose the first one, for example, and take a look where this request is located. So this is a reference from server response to request and from one big array. So let's figure out where is this array located. And with command v8 find refs value and address of this array, we can find the parent object. And this is profile middleware with a request property. So we found which object holds memory. My suggestions. Control the life cycle of objects. So you need to know where your object was created and where it will be removed. Trace work of garbage collector. And if you're not sure about the behavior of JavaScript behavior, maybe in case of closures, you can download and use D8, which is a debug 8 for V8, and check the JavaScript behavior. Call JavaScript manually or write a memory usage test using leakage. And create heap dump and core dump to investigate and find the problem. So finally, we lose performance with the growth of functionality until it became critical for us. And after all those improvements, we achieved and increased our performance by half from the original baseline. And to prevent a situation like this one, you can choose my tips, my suggestions, because Node.js was created as a fast performance platform, and we, as end users, should develop fast performance applications. That's all. Thank you.